Today's lesson is about direct variation. Your learning objective says, I can correctly calculate the direct variation of a situation. All right, there's a lot of information on this page about direct variation. You should be writing your notes in your interactive math notebook. So first and foremost, it's important for us to understand that we're talking about a proportional relationship where you have a constant rate of change. So when you have a constant rate of change and you add proportionality, you will get direct variation. Now keep in mind, proportionality has two parts to it. It's got to be linear, which is taken care of with the constant rate of change issue, but it also has to pass through the origin, or 0, 0. Direct variation is also known as slope, but without the y-intercept in the famous y equals mx plus b formula. Sometimes direct variation is shown as a k, but we want to be consistent. So since we're going to be moving into the slope formula, we're going to call it m. So our equation will be y equals mx. Eventually, we'll add that plus b when we have to adjust things a bit. Right now, this is where we're going to stay. And the graph would look like a straight line going through the origin. Let's jump right in. Oh, no pun intended. We are talking about a backyard pond. Anyway, as it's being dug, the depth of a hole for a backyard pond is recorded in this lovely table. So the independent variable is time, the dependent variable is hole depth. So what I want you to do in your interactive notebook is I want you to graph the data. Tell me, do you think there's a constant rate of change, and is the graph proportional? Then, if you feel like you can write the equation, you can go for it. We did talk a little bit about equations in the last video. And then, if you feel like you're extra great today, I want you to try to predict how long it will take to dig 36 inches of depth. So pause me while you're working and come back when you're ready for checking. All right, so I've got my graph set up. I have my title, pond. I've got my independent variable on the bottom, time. Should be in minutes. And then depth is going to be in inches. All right, so when I start to graph this, in 10 minutes, the hole depth will be 8. And it is extremely difficult to graph on this iPad, but I'm doing my best. In 20 minutes, the hole depth will be 16 inches, so that'll be here. In 30 minutes, 24 inches. And in 40 minutes, 32 inches. Should be right here. All right, so if I only connected those dots, which wasn't very good, let me try that again. I only connected those dots. That's a little bit better. This is what my graph is going to look like. Is there a constant rate of change? Well, yes, because if there's a constant rate of change, you will get a linear graph. Plus, if I wanted to figure that out, it appears that I am skip counting by 8 every time on the hole depth. So my change in y is 8, and I am skip counting by 10 every time on my change in x. So actually my constant rate of change would be 4 inches for every 5 minutes. And then is it proportional? Well, if I had a straight edge and I continued my line, would 0, 0 be part of this situation? Well, I can do it a couple ways. My graph is a little wonky. I did not use a straight edge, but I could go backwards from where I am on the table. And so if I went back 1, instead of adding 8, I would subtract 8 from this and I'd be at 0. And on this one, if I went back 10 minutes instead of adding 10 minutes, I'd be at 0. So it looks like my graph should go through the origin, but when I checked it with my table, it definitely will. So yes, it is proportional because it is a straight line and it will go through the origin. So keep in mind that my equation, y equals mx, that m is my slope. That m is my multiplier or my constant rate of change. And so it looks like I'm going to take y equals 4/5 times x. Now on this last one, my prediction, I could do it a couple ways again. I could extend my line if I had a straight edge and I was being more careful than I'm able to be on the iPad. I could get a good idea of how long it's going to take to dig to a depth of 36 inches. Or y is 4/5 of x. So my whole depth is y. I want that to be 36. When will this work out? When I solve this, the opposite of multiplying by 4/5 is dividing by 4/5. Dividing by 4/5. That cancels. X will be at 45 minutes. I could check that on my graph. 45 minutes would be 36 inches. And I could even check it with my table because I wanted the depth to be 36, which was half of what I was skip counting by. So if I added half of what I was skip counting on this side, I'd also get 45. All right, let's try another one, and this data is for apples. Notice I don't have any paper for us to graph on, so we're going to use just this table. And I want you to tell me, does it appear that there is a constant rate of change, and do you think the data is proportional? Then I want you to do your best to write an equation that relates the cost and the weight. And finally, use that equation to predict how much 5 pounds of apples would cost. And when you're ready for checking, you're going to come back to me. So go ahead and pause me now. So in an earlier video, we found out that we can do our rate of change by taking the change in y over the change in x. So it appears that we are skip counting by 75 hundredths, or in this case 75 cents because we're talking money, for every half pound of apples. All right, I can simplify that a bit. Just using my number cents, if it's 75 cents for a half a pound, and I really want to know 1 pound possibly, I would simply double everything. So if it's 75 cents for a half a pound, it would be $1.50 for a full pound. And I kind of like it like that because then I can use my multiplier as just a whole number instead of having a fraction with decimals involved. All right, so does it appear there's a constant rate of change? Yes. My y value is increasing by 75 cents every time. My weight is increasing by half a pound. Is the data proportional? Well, just like we did before, we could work our way backwards from our first entry in our table. So if we are adding 0 and 5/10 pounds every time, if we simply subtracted that to get the one above, we'd be at 0. And if we were adding 75 cents each time and we worked backwards to get the table entry prior to what I'm showing you, we'd be at 0. So as long as we have a constant rate of change, that's going to give us a linear graph. And if that linear graph goes through the origin, then yes, it is proportional. So our equation is going to be, let me change colors, y equals mx. Remember, m is our slope, our rate of change, our direct variation, whatever it is you want to call that, that's our multiplier. And so I liked having this format because now I can just say y, or the cost, is $1.50 times the weight of the apples. And so now that I have that, I can start substituting. I have to remember the weight is the X number. So the cost of the apples would be $1.50 times, in this case, 5, which would cost $7.50. Our next problem has a graph again. So this one is about the length of a spring stretching. So it varies directly with the amount of weight attached to it. When an 8-ounce weight is attached, the spring stretches 2 inches. And so I have started a table here for us. I want you to graph the data, write an equation that relates the weight and the amount of stretch, and estimate the stretch of the spring when it has a 20-ounce weight attached. So you will pause me while you are working and then come back when you're ready for checking. All right, so you'll notice that I have the beginning of my graph here. I have my title called Spring. I have my independent variable of weight and my dependent variable of stretch. So I'm going to try and graph this the best I can on the iPad. So at first we start at 0, 0, which is the origin, so it's right here. And then we go 8 ounces and 2 inches, so that's right here. And finally, 16 ounces and 4 inches is right here. So if I had a straight edge, I would certainly use it, but I'm going to eyeball a straight line through there. All right, so we've graphed the data. Because this data has direct variation, which means that it is linear. Whoops, let me try that again. Linear. And it is proportional because it goes through the origin. I can use the equation y equals mx. Remember, m is your constant rate of change, or your slope, or your direct variation. It's your multiplier. To figure that out, I would need a change in y. So if I look here, it looks like my change in y, I'm adding 2 every time. And then I would need a change in x, and it looks like I'm adding 8 every time. So my constant rate of change would be a change in 2 inches over 8 ounces every time. And I can put that in simplest form. I can say it is 1 inch of stretch for every 4 ounces of weight. And once I know that multiplier, I can just plug it in. Y equals 1/4 times x. So that is my equation. Now I'm going to use that equation to help me figure out the stretch of the spring when it has 20 ounces of weight. Well, keep in mind that the weight right here, that's my independent variable. That's my x. And so I would use my equation, and instead of an x, I'm going to put my 20-ounce weight. So it looks like y is going to be 5 inches. Now I can check that a couple of different ways. Let's look at my table. So if I wanted it to be 20 ounces right here, if I added another entry to my table, I would only be going half my change in x. If I'm only going to go half my change in x, then I am only going to go half my change in y. So instead of going 2, I'm going to go 1, and I would be at 5. Another way to check it, I can go up my graph 20 ounces. I'd have to extend my line a bit to where my line is, and then I could take a sharp left and come over here, and indeed there should be a 5 right there. So there's a couple of ways for us to check our work. All right, last problem for today. I want you to think about this situation. Tyler charges his customers $10 per week plus $5 every time he walks their dogs. What would the sketch of the situation look like? Is there a direct variation? Construct a viable argument to support your decision. I want you to make your sketch in your interactive math notebook. decide if you think there's going to be a direct variation and make your argument. And when you're ready, I want you to come back and check to see what I thought. So I've set up my sketch. I've got dog walking as my title. My money depends on how many times the dogs are walked. So walks is my independent, money is my dependent. So Tyler's going to charge his customers $10. So that's our starting point, $10, and then $5 for every walk. I think that my graph is going to look something like that. I might have my proportions off by a bit. And so this cannot be a direct variation. The answer is no. The reason it cannot be a direct variation is that although this data would be linear, it will never pass through the origin. And therefore, not be a direct variation. So this is one of those cases where we would actually have the y equals mx plus b equation. This whole lesson we've kind of ignored this plus b. That was how we adjusted things. So actually, the equation for this would be he's going to charge $5 for every walk. That's our multiplier. And $10 per week.